In this video, we will discuss about the signal detection process when we are using binary signaling, and that is binary unipolar signaling. And we will do so when this transmitted signal has been corrupted with additive white Gaussian noise, where the Gaussian noise has the Gaussian distribution as shown in this figure, with the mean value equal to 0 and some standard deviation. In this case, this particular plot of the Gaussian PDF is for the standard deviation equal to 1. It could be any standard deviation sigma. So when the transmitted signal, which is represented as a binary unipolar signal, is corrupted with zero mean Gaussian noise, what should be the detection process, or what is the technique we are going to use to detect the received bits by observing the received signal that has been corrupted with Gaussian noise. And then towards the end we will also talk about the now we will derive an expression for the average probability of error when we use such a technique to detect the bits. Okay, obviously we want the error probability to be as small as possible, so we want to devise a mechanism which will achieve such low error probability. And we will see that even though we want the error probability to be ideally 0, there is going to be some non-zero value for the error probability, but we want to have the mechanism devised in such a way that this non-zero error probability is as close to 0 as possible. But before we even begin with the analysis of the detection process in the binary unipolar signaling case, let us quickly recall what we defined earlier as the Q function. So the Q function, if we recall, is the area under the Gaussian PDF's tail from some threshold value up to infinity. So let's say we choose some threshold value, which is say which is some value between 1 and 2. Then this area under the Gaussian PDF's tail from V up to infinity, we call this area as the Q function, Q of V by sigma. And these values are available to us as a table which we'll use in our calculations. Okay, now the important thing to note here is that when we compute this value for V, the threshold, the starting point of this area to compute from V to infinity, we need to ensure that that value corresponds to the threshold when the Gaussian PDF is centered on 0. You see here, the central value is 0. So if it is not centered on 0, if we have a Gaussian PDF which is not centered on 0 and we know some value for this threshold, then we need to shift that entire PDF by an amount such that it becomes centered on 0, and correspondingly that threshold will also get shifted by the same amount so that the Q function is computed correctly. Okay, so the Q function applies to the Gaussian PDF that is centered on 0, which has a mean value of 0. And then once we have that with the central value as 0, then we can choose any threshold which we can call as V, and from V to infinity we compute the area under this PDF from V to infinity, and that is called as the Q function, denoted as Q of V by sigma. So suppose if this V is if this V is say 1.5, then it's from 1.5 to infinity under the Gaussian PDF, which has 0 mean and some standard deviation sigma. So if it's 1.5, we'll write that as Q of 1.5 by sigma. And similarly, it can be any other representation. For example, if V is A by 2, okay, some A by 2, let me write that properly, A by 2, then the corresponding q function, in place of v, we will write a by 2, and we have the sigma in the denominator. So we call that as q of a by 2 sigma if v is equal to a by 2, right? So in the case of v equals a by 2, we write it as q of a by 2 sigma. Then the next important thing that we also notice in the Gaussian PDF is that because the Gaussian PDF is symmetric, so if we have an area computed on the negative tail, on the other tail of the Gaussian PDF, the Gaussian PDF has two tails, one to the right side and another one to the left side. So if we have the same v on this side, on the negative side, so let's say we are computing the area of the Gaussian tail from minus infinity to minus v, this area, that is also the same as this by the symmetric nature of the Gaussian PDF. So this is also equal to these numbers, okay? So if it's minus infinity to minus v is the same as v to infinity. So if it's minus a by 2 here, then it's equal, the area here is the same as q of a by 2 sigma, right? So these areas are the same. So this is equal to this one. So they are equal due to the symmetric nature of the Gaussian PDF. And again, this is something which we would be using in computing the error probability for our analysis. When we compute the error probability for signal detection with unipolar, as well as later on for polar signaling, and then we will also extend these ideas to emery signaling. So at the moment we are focusing on binary signaling, where we have only a 0 and a 1. We have a bit 0 and a bit 1. Now later on, when we extend it to emery signaling, we will have symbols which will be combinations of bits. So with binary signaling, we have a 0 and a 1, which will be each represented by a voltage level. So we have only 2 voltage levels in binary. But with emery, we will have m different voltage levels, each of which would be corrupted by Gaussian noise. Okay, so we need to understand and remember what this q function means. So in the analysis, we will talk in terms of the q function, and later on in the tutorial class, we will discuss about the table from which the q function can be read out. Okay, let us now look at the unipolar signaling case and devise a mechanism for detecting a signal which is represented by a unipolar signal, and when it has been corrupted by white Gaussian noise, additive white Gaussian noise with 0 mean value. In unipolar signaling, and of course we are dealing with the binary case here. Because it's a binary, we have a 1 and a 0. So we have a bit 1 and a bit 0. We have only 2 symbols, and that each symbol is equal to a bit. And for the binary one, in unipolar signaling, we represent a binary 1 as some positive voltage, which we will call as plus a volt, and a binary 0 or bit 0 is represented as 0 volt. So the waveform that we are going to transmit is going to be a rectangular waveform, which is going to have 0 volt every time the transmitted bit is 0, and a positive a volt. That a can be 5 volt or 5 or 10, whatever, depending on the hardware that we're going to use. So in general, we just say some positive voltage a volt. Okay, so that's our transmitted signal. And to this transmitted signal, the 0 mean Gaussian noise will get added, and the received signal would be the sum of the transmitted signal and noise. So we'll have this is our transmitted signal x, that is equal to 1 or 0, and when it's 1 it is plus a volt, and when it is 0 it is 0 volts. So the received signal is going to be y equals the transmitted signal plus noise, where the noise n is 0 mean Gaussian noise with standard deviation sigma, and it could be any value of sigma, but the mean value mu is equal to 0. So 0 mean, that is mu equal to 0. So that means the Gaussian PDF is centered on 0. So let us have a look at the plot of the transmitted and received waveforms in such a case. So we have the received signal, which is the sum of the transmitted signal plus noise, where the noise is 0 mean Gaussian noise with standard deviation sigma. Okay. Now for unipolar signaling, we have a 0 represented as 0 volt and the 1 as some positive volts, and that gives us a level separation between the two voltage levels as A volt. So the level separation between 0 and 1 is A volt. Okay, we will be keeping this level separation to be A for all our examples. Later on, when we do instead of unipolar signaling, when we use polar signaling as well, and because we want to compare unipolar with polar signaling, we will keep the level separation in that case as well as A. Okay. Now what we will be doing is we will be devising a method to detect the received signal, which is to observe this blue waveform, which is the received signal Y, and then decide whether it is representing a 1 or a 0 by drawing some decision rule, and then we will decide whether the received bit is a 1 or a 0 by applying some decision rule. Now clearly, if you look at this particular figure, we can have a threshold which is exactly halfway between 0 and A volt. So if we draw a level between 0 and A, exactly halfway there, and then say if the received signal Y is greater than that level, we will decide in favor of 1, and if it is less than that level, we will decide in favor of 0. So we can have a threshold. I'll use a color like this. Okay, so that could be our threshold. Oh, let me draw it a bit neater. So that could be our threshold, which should be halfway between the voltage levels of 0 and A. So if we have this as A by 2, we can use this as a basic rule to decide whether the received signal is representing a 1 or a 0. So you'll say if the received signal Y is greater than this threshold, we will decide it's a 1, and if it is less than the threshold, we will decide it as a 0. Right? Now, what would the PDF of the received signal look like in such a case? So we have two cases here. One is when binary 1 is transmitted, or bit 1 is transmitted. The received signal is A volt plus the noise that is getting added. And whenever we are transmitting a binary 0, the received signal is X, which is 0 volt plus the noise. So it's just basically represented by noise. So the received signal is going to be received signal is Y equals X plus N, which is going to be Y, because we have two cases for X. X can be 0 volt if the bit transmitted is 0, and 1 volt if the bit transmitted is binary 1. So Y is equal to the voltage level for 1, which is A, plus noise if 1 is transmitted, and it will be 0 plus noise, which is simply equal to the noise if 0 is transmitted. So we have two cases here for the received signal, and N obviously is the Gaussian noise which has a mean value of 0. And when this Gaussian noise is getting added with some constant, the mean value is going to get shifted. So the received signal's PDF when a 1 is transmitted is going to be the Gaussian PDF of the noise, but the mean value shifted to A volt. That means it will be centered on plus A rather than being centered on 0. When a 0 is transmitted, the received signal is exactly the same as the noise signal, so the PDF of the received signal will be exactly the same as the PDF of the noise signal. So we'll define what is called as the conditional PDF, probability of Y given when a 1 is transmitted, on the condition that a 1 is transmitted. So it's the conditional probability of the received signal Y given the condition is bit 1 has been transmitted, is the noise PDF P of n, but the noise PDF is now centered on A. It will be the same as P of n minus A. So P of n is nothing but the noise PDF which we have shown here. This is basically P of n, which is centered on 0. This will get shifted by A, so it will be, instead of being centered on 0, it will be shifted and it will become centered on A. So it will be shifted to the right by A because we have added a constant A to the 0 mean Gaussian noise. So the noise PDF when a 1 is transmitted is going to be the received signals PDF when a 1 is transmitted will be the noise PDF shifted to the right by A, so that the received signals PDF when 1 is transmitted is the Gaussian PDF centered on A volt. But when a 0 is transmitted, the received signals PDF on the condition that a 0 is transmitted, because a 0 is represented as 0 volt, so the received signal Y is just 0 plus noise, which is simply noise. So it is going to be exactly the same as the noise PDF, which will be centered on 0. So these are the conditional PDFs. Conditional probability density functions of Y when 0 is transmitted and when 1 is transmitted. So you have two different conditions, whether the transmitted bit is a 1 or a 0. So accordingly, the conditional PDF of the received signal Y would be different depending on whether 1 has been transmitted or 0 has been transmitted. Let us depict those PDFs graphically. So here we have the conditional PDFs of the received signal when 0 is transmitted, which is given by the blue PDF. So when 0 is transmitted, it is the same as the noise PDF centered on 0 because we have added 0 volt to it, so nothing changes. So it's 0 plus noise is simply the noise, and the noise PDF is 0 mean Gaussian noise centered on 0. And when a 1 is transmitted, to the noise PDF, a constant value of A is getting added, so the PDF gets shifted by A volt, and so when you shift this by A volt, it will come to A volt. Here again, this is A volt. Okay, forget about the numbering. So we have this as our A volt. Okay, let me write that clearly. So we'll just ignore these numbers for the moment. Okay, so we'll keep the 0, by the way. So the conditional PDF when 0 is transmitted is centered on 0, and the conditional PDF of the received signal Y when 1 is transmitted is centered on A. So this is P of Y on the condition that 0 is transmitted, and this is P of Y on the condition that 1 is transmitted, as has been shown in these legends here. Okay, so the blue curve represents the conditional PDF when 0 is transmitted, and the red represents the conditional PDF when 1 is transmitted. Now, the threshold that we are going to use for making a decision is halfway between 0 and A, which is A by 2. So the threshold in the case of PDFs, halfway between 0 and A will come exactly at this point of intersection between 0 and a, which is a by 2. So because of the symmetric nature of the Gaussian PDFs, this intersection of these PDFs will happen exactly between will happen exactly halfway between 0 and a, which is exactly at a by 2. So the intersection point here is going to be a by 2. So that's the threshold that we are going to use to make our decision. So let's first define what we call as the decision threshold now. So the decision threshold is the point of intersection of the conditional PDFs. Of the received signal y. Okay, and in this case it is going to be exactly halfway between 0 and a, which is equal to a by 2. So the threshold we are going to choose it as a by 2, which is exactly the halfway point between 0 and a. And in the case of the PDFs, that corresponds to the point of intersection or the x-axis value at which the two PDFs intersect, and that is a by 2 as well. Okay, so we have now defined our decision threshold. Next, we define what we call as the decision rule. Now, the decision rule would be as if the received signal y is greater than the threshold, our threshold is a by 2, decide it as a 1. Decide 1. If the received signal y is less than a by 2, then decide as 0. Occasionally, but very rarely, it will be the case that the received signal is exactly equal to the threshold, exactly equal to a by 2. In that case, we have no choice. We have to decide, we have to just arbitrarily guess whether it's 1 or a 0. So in terms of the rule, we will give it in favor of either a 1 or a 0. We can put it in one of those two conditions. So I'm just going to put it in place of the 1. So if it is greater than or equal to a by 2, that is the threshold, we will decide it as a 1. If it is less than the threshold, we will decide it as a 0. And this equality, equal to condition, we could have put it here also, but we cannot have it in both the places. That would not make a logical decision rule. Okay, so if it is a by 2 or more, we will decide it as 1. If it is less than a by 2, we will decide it as a 0. So that's going to be our decision rule. Now, once we have made this decision rule, the received signal, the receiver side will check whether the received signal is greater than this a by 2, and if it finds to be greater than a by 2, it will decide it as a 1, and if it checks and finds it to be less than a by 2, it will decide it as a 0. But occasionally, there could be a situation where we transmitted a 1, but the received signal is less than a by 2 because of the noise, and the receiver thinks it's a 0. So a 1 has become a 0, or vice versa. Maybe we have transmitted a 0, but the received signal ends up being greater than a by 2, and the receiver decides it as a 1, in which case again it makes an error. So if there is a difference between what is transmitted and what is received, then that constitutes as error. So the error happens if 1 is transmitted and and the received signal y is less than a by 2, the receiver, I'm going to just denote Rx as the receiver, the receiver decides it as 0. So what happens is we transmitted a 1, but the receiver thinks it's a 0, so that's an error. A 1 has become a 0. And it could also be possible that we transmitted a 0 and the received signal y is greater than or equal to a by 2, then the receiver decides it as 1. So now here the 0 has become a 1, which is also an error. Okay. Now to distinguish these two cases, when a 1 becomes a 0, that means a 1 has got corrupted. We will call it the probability of a 1 becoming a 0. We will call it as the probability of error when 1 is transmitted. So we will denote it as PE1. And similarly, when a 0 becomes a 1, that's an error corresponding to 0. So we'll call the corresponding probability as PE0. So we have two different error probabilities. One is the probability of error, that is 0 is transmitted and the receiver thinks it's a 1, or the second one is PE1, which is 1 is transmitted and the receiver thinks it's a 0. So the corruption of a 1 is PE1, the corruption of a 0 is PE0. That's the notation we are going to use. Now when we transmit a large number of bits, some of the 1s could have become 0 and some of the 0s could have become 1, and then we need to find out what is the average probability of error. Now to compute the average probability of error, we will look at the conditional PDFs of the received signal, and then using the threshold we will try to deduce or analyze what are the values or what are the expressions for these probabilities PE0 and PE1. So here we have our conditional PDFs once again, and the conditional PDF of y when 0 is transmitted is centered on 0, and when a is transmitted is centered on, when 1 is transmitted is centered on plus a volt. So the blue PDF is the conditional PDF when 0 is transmitted, which is P of y given 0, and the red one is the conditional PDF when 1 is transmitted, right? So I'm just reiterating this, and that's P of y given 1. So we have our conditional PDFs. Next we have our decision rule. Which is the intersection of these conditional PDFs. Let me use a thicker line. So that's our decision threshold, and our decision rule, as we stated earlier, if the received signal y is greater than or equal to the threshold, the receiver will decide it as a 1. If it is less than the threshold, the receiver will decide the received bit as 0. So our threshold is a by 2. That's a by 2. And any received value which is greater than a by 2 will be decided as 1, and anything that is below this threshold will be decided as 0. Now suppose that we transmitted a bit 0 is transmitted, which corresponds to this blue PDF. There is some part of this PDF which is to the right of the threshold. That means there is some probability that we transmitted a 0, which gives us this PDF for the received signal, but the received signal is greater than this threshold. So that would constitute an error. When we transmit a 0 and the received signal is greater than the threshold, that area under this curve here from a by 2 to infinity will constitute the error probability when a 0 is transmitted. So the area here, which is this area, and by the way, this does not become 0, right? It becomes smaller and smaller, but it goes on till infinity and becomes 0 only at infinity. So this area here denotes the error probability when 0 is transmitted, which we call as PE0. So there is a chance that we transmitted a 0, but the received signal is above the threshold and the receiver thinks it's a 1. That corresponds to an error when 0 is transmitted, which we call PE0. Similarly, we could have transmitted a 1 and the received signal ends up being less than the threshold and the receiver thinks it's a 0. So the area under the Gaussian PDF for the received signal when 1 is transmitted, which lies to the left of the threshold, denotes the error probability for a binary 1. So the area here to the left of the threshold, this area is the error probability when a 1 is transmitted. So we can see the error probabilities graphically in terms of the areas under the Gaussian PDFs. Now we earlier discussed about the Q function, and we are going to represent these areas as the Q function, and that is why we have been introduced to the Q function earlier. So this PE0 will start with the error probability for 0, which is PE0 is the area under this PDF P of y given 0 to the right of a by 2. So area means integration, right? So it's nothing but the integration under this blue PDF, which is P of y given 0, the conditional PDF of y when 0 has been transmitted, dy, and the limits of integration are from a by 2 to infinity. It is to the right of a by 2, so it's from a by 2 to infinity. So that's our error probability when 0 is transmitted, which is nothing but, if we go back to our Q function, so the Q function clearly says if we have some threshold, which we can call as V, when the PDF is centered on 0, whatever is that V, we can put it inside this Q of V by sigma. So coming back to our analysis here, our cutoff point is a by 2, and this blue PDF is indeed centered on 0. So for the area under the blue PDF to the right of a by 2, it is simply the cutoff here is a by 2. It is Q of a by 2 sigma, right? Which is simply equal to Q of a by 2 sigma. So instead of V, we have a by 2. So that's the error probability when 0 is transmitted, which is P0. But the error probability when 1 is transmitted is the area under this red PDF to the left of a by 2. But we can't just write it as the Q function because this red PDF is not centered on 0. It is centered on A. So we need to shift this and make it centered on 0. So we have to shift this red PDF to the left by A. So when we shift this red PDF to the left by A, the central value will become 0 for the red PDF also, and correspondingly the limit here will also get shifted by A. So instead of a by 2, it will go back by A, so it will come to minus a by 2. So from 0 to a by 2, that's half A, right? So if you go to the left by A, that means this a by 2 will come to minus a by 2, and this PDF will be centered on 0. So let's write that. Okay, the error probability when 1 is transmitted is the area under the red PDF, which is P of y given 1 dy, to the left of a by 2, which is from minus infinity to a by 2. Let me write that clearly. To a by 2. So that's the error probability for when a 1 is transmitted. Now, because it is not centered on 0, we need to shift this to the left by a to make it centered on 0. So since it's the area that we are computing, it doesn't matter whether we compute the area. For example, if you want to compute the area of the surface of a table, it doesn't matter where we keep the table in the room, right? Wherever we keep the table in the room, the area of the surface top of the table is going to be the same. Similarly, it doesn't matter. We are interested in finding the area to the left of this threshold. Whether we shift it to the left or right, it doesn't matter, as long as we accordingly shift the limits or the threshold value as well. So we are interested in making this centered on 0, simply because that area can then be availed or taken from a table which is readily available for us. So we will just shift this to the left and accordingly shift the limits also to the left. So we can write that as P of y given 1, shifting to the left is plus, and the amount of shift is a. So we are shifting the entire PDF by a to the left. So this red PDF will get shifted to the left and become centered on 0. Since we have shifted the PDF to the left, this threshold will also get shifted to the left by a. So it will now come to minus a by 2. So and minus infinity shifted further to the left remains minus infinity. And a by 2, when we shift it to the left by a, will become minus a by 2. So that corresponds to the threshold coming up here. Okay, so that would be the limit minus a by 2, and we are going to find this area here, right? So by the symmetric nature of the Gaussian PDF, so now it's like the PDF centered on 0, but the area computed to the left of minus a by 2, which is the same as the area from a by 2 to infinity, because the Gaussian PDF is symmetric about the mean value 0. So this area is the same as this area, which is basically equal to q of a by 2 sigma. So minus infinity to minus a by 2 to infinity is the same. So we can now swap the limits of the integration. So that will become equal to integral a by 2 to infinity p of y given 1 plus a dy, which is also equal to q of a by 2 sigma. So we have now got the error probabilities for 0, which is PE0, that's equal to q of a by 2 sigma, and for 1 it is PE1, which is also equal to q of a by 2 sigma. Now we'll just keep it as the q function now, and we will come to how to evaluate this q of a by 2 sigma and to compute it from the table. We'll talk about this later, but just understand that this q of a by 2 sigma represents the area under the Gaussian tail. Right. Next, what we want to do is we want to find the average probability of error by combining the error probability of 0 and 1. So we now have the error probability when 0 is transmitted is PE0, which is equal to q of a by 2 sigma, and the error probability when 1 is transmitted is also equal to the q function of a by 2 sigma. Now we will compute the average error probability, which we will simply call as PE. Now the average error probability is the probability that we transmit a 0, so P0 is the probability of transmitting a 0 multiplied by the probability that there is an error with the 0. So it is P0 into P0. This error with a 0 will happen only when we transmit a 0. If we don't transmit a 0, this error will not occur at all. Pe0 will not occur if we don't transmit it a bit 0. So the probability that we transmit a bit 0 and the probability that the 0 bit has become a 1, so that means there's an error in the 0. So and in probability means multiplication. The probability that we transmit a 0 and there is an error in that 0, so that's P0 into Pe0, or in probability is plus. We transmit a 1, so the probability that a 1 is transmitted and there is an error in the transmitted 1. So that will give us the average probability of error. Now, when we did our threshold decision, the threshold value for the decision making, we chose the threshold exactly halfway between 0 and 1, right? Halfway between the voltage levels for 0 and 1. So that means we are giving 50% of the space for a 1 and 50% of the space for 0. And that choice of choosing the threshold exactly halfway is optimum when we assume that the 1s and 0s have equal probability of being transmitted. That means if we transmit a large number of bits, say 1 million or 10 million bits, approximately half of them are going to be 1s and approximately half of them are going to be 0s. So we say that the 1s and 0s are equally likely. And in such a case, the optimum threshold value is halfway between the voltage levels. So this choice of choosing the threshold to be halfway is on the assumption that the 1s and 0s are equally likely. So that means the probability of transmitting a 0 and the probability of transmitting a 1 is equal. So that will correspond to half, right? So let's mark this where P0 and P1 are the probabilities of transmitting 0 and 1 respectively. And when we have the 1s and 0s to be equally likely for equally likely 1s and 0s, the probability of transmitting 0 is equal to the probability of transmitting 1, and that is equal to half. So both have 50% chance. That's what we mean by equally likely. So if we transmit a large number of bits, almost half of them would be 1 and half of them would be 0. So we'll substitute this in our expression for the average probability of error. So that will give us the average probability of error is P0 is half and Pe0 is the Q function, Q of A by 2 sigma, plus P1 is half and Pe0 is, and Pe0, that's Pe1, the second part, is also Q of A by 2 sigma, right? So we can take this half as a common factor. So half into Q of A by 2 sigma plus Q of A by 2 sigma, which will become half into Q plus Q will become 2 times Q of A by 2 sigma. And by the way, this Q function is nothing but the area under the Gaussian PDF tail, right? So an area plus another area of the same value is going to be 2 times that area. So the half into 2 is 1. So we end up getting the average probability of error is Q of A by 2 sigma. So the average probability of error, PE, for unipolar signaling is equal to the Q function of A by 2 sigma. So if you notice here, sigma is a variable that depends on the noise. It is the standard deviation of noise. 2 is a constant. So this probability of error depends on A here. And what is A? A is the level separation between a 0 and a 1. So if the noise is stronger, we need to keep this level separation much bigger. If the noise is weak, we can keep the voltage level for 0 and 1 close to each other. So the error probability depends on the level separation between the 0 and 1. Okay, so that's the expression for the average error probability for unipolar signaling, that is binary unipolar signaling in the presence of additive white Gaussian noise, when the ones and zeros are equally likely to be transmitted. That means the probability of transmitting a 0 and the probability of transmitting a 1 is equal to half. Okay, in the next video we will be doing the similar analysis for polar signaling. So rather than unipolar signaling, where we had a 0 represented as 0 volt and a 1 represented as a positive volt, in the next video we'll talk about polar signaling, which is also called as bipolar signaling, where the 0 would be represented as a negative voltage level and 1 represented as a positive voltage level. So we have two polarities, negative and positive, so that we call it as polar signaling. And we will do a similar analysis to find the average error probability for polar signaling. And in order to be able to compare our analysis for unipolar and polar, even in the polar case, we will ensure that the level separation that we choose between the voltage level for 0 and the voltage level for 1 is the same A. Okay, so we will discuss about that in the next video.